Okay, I'm going to do some sample problems, some even numbered problems for you so that you can see how I approach these. Some of these are pretty simple, but the last one is pretty complicated, pretty tedious. It's easy to do, but it's a little bit tedious. So let's share the um, iPad, because that's where I have this. Hello. Here we go. All right. So we're looking, let's look at, these are even number problems. So for two conductors having net charges of uh, plus 10 microcoulombs and minus 10 microcoulombs have a potential difference of 10 volts between them. A, determine the capacitance of the system. Okay, so if you have 10 microcoulombs on one, I'm going to call it a plate, you're going to have minus 10 microcoulombs on the other. Remember I said once you build up charge electrons on one, you're going to have a paucity of electrons. You're going to have a lack of those electrons on the other side, and so it's going to have a positive. So on one plate is 10 microcoulombs, the other is minus 10 microcoulombs, and there's 10 volts between them. So the capacitance of the system, it's just C equals Q divided by delta V, so it's 10 microcoulombs divided by 10 volts, and you end up with 1 microfarad. Now, what is the potential difference between the two conductors if the charges on each are increased to 100 microcoulombs? Well, the capacitor is not going to change. It's determined by the geometry. So it's a 1 microfarad capacitor. So the delta V is equal to the charge, 100 microcoulombs, divided by the capacitance, 1 microfarad, and you're going to end up with 100 volts. Okay, that takes care of that one. Now the next one, and number 4, this is using the geometry to determine a capacitor. An air-filled parallel plate capacitor has plates of area 2.3 centimeters square centimeters separated by 1.5 millimeters. Find the value of its capacitance. The capacitor, okay, find the value of its capacitance. Now, if we're going to do this, we need to convert everything to meters. So using this equation, 25 3, this is what we're going to use. The C equals epsilon 0 times the area divided by the distance between the plates. So C equals E sub 0 times 2.3 centimeters squared. Now to convert it, it's 1 square meter for 10 to the 4th centimeters squared divided by 1.5 millimeters, and that's times 1 meter per 1,000 millimeters. So it's epsilon 0 times 2.3 times 10 to the minus 4 square meters divided by 1.5 times 10 to the minus 3 meters. So if you plug in the value, the epsilon 0, 8.854 times 10 to the minus 12, Coulomb squared, Newton meters squared times 2.3 times 10 to the minus 4 meters squared, divided by 1.5 times 10 to the minus 3, you'll end up with 1.36 times 10 to the minus 12 farads. We call that 10 to the minus 12 is pico. Minus 6 is microfarads, minus 9 is nanofarads, and minus 12 is picofarads. So it's 1.36 picofarads. Now the charge is Q, that's B. The capacitor is connected to a 12-volt battery. What is the charge on the capacitor? The charge on the capacitor is Q is C equals delta V, so it's 1.36 picofarads times 1.2, not 1.2, 12 volts, and you end up with 1.63 picocoulombs. Now C, what is the magnitude of the uniform electric field between the plates? Delta V is equal to ED, the electric field times the distance. So E is equal to delta V divided by D. So it's 12 volts. That looks like 124, but it's not. It's that's volts. 12 volts divided by 1.5 times 10 to the minus 3 meters equals 8,000 volts per meter. And that's the completion of problem 4. Now problem 7. Find the equivalent capacitance of a 4.2 microfarad capacitor and an 8.5 microfarad capacitor when they are connected A in series and B in parallel. Well, so you have a 4.2 microfarad capacitor and an 8.5 microfarad capacitor. This is for later. I mean, we have to calculate it first. Now let's do it the long method. Let's do it the book method. 1 over C equivalent is equal to 1 over 4.2 microfarads plus 1 over 8.5 microfarads. Now, I wasn't going to take the trouble to find a common denominator. I just did 1 over 4.1 over, I took 4.2 times 10 to the minus 6, inverted it, and I added it to 8.5 times 10 to the minus 6, inverted it, and got the sum. And you end up with 3.56 times 10 to the 5th, but it's 1 over farads. Now, if you take the inverse of that, you have to take the reciprocal of that. That's not the answer. 10 to the 5th, you should not ever end up with a capacitance of 3.56 times 10 to the 5th. You have to take the inverse of that. So C equivalent is the inverse of that, and you end up with 2.81 microfarads, and that's the equivalent circuit that I put there. Now, that's the long method. That's the book method. I showed you in one of the lectures a shortcut method. C equivalent is equal, and you don't have to take the reciprocal of anything. You just multiply it, but multiply and divide by the sum. The problem is this only works when there's just 2 capacitors. You can't use this for multiple capacitors. So the C equivalent is equal to C1 times C2 divided by C1 plus C2, the product divided by the sum. So the equivalent is 4.2 microfarads times 8.5 microfarads divided by 4.2 microfarads plus 8.5 microfarads. So you end up with 3.57 microfarads squared. We don't really use microfarads squared, but it will come out in the calculation. It's divided by 12.7 microfarads, and lo and behold, you end up with 2.81 microfarads, the same value that we got up above. I think it's a little easier to do it this way, but again, this only works when you have just 2 capacitors. Fortunately, the microfarad squared is divided by microfarads, and you're just going to end up with microfarads. Now, let's do it in parallel. And parallel is very easy. You just add them. So the C equivalent is 4.2 microfarads plus 8.5 microfarads, and you get 12.7 microfarads. You already got that total in the denominator here, so you already know that value. So it's 12.7 microfarads. Now here's the real killer problem. It's not really a killer. It's tedious, but it's not difficult. So number 12, find the equivalent capacitance between point A and B for the group of capacitors connected as shown in figure 2512. Take C1 equals 5 microfarads, C2 equals 10 microfarads, and C3 equals 2 microfarads. And part B is what charge is stored on C3 is the potential difference between the points A and B is 60 volts. So the first thing I did, I recognize these circuits, but if you're new to this, you might have difficulty seeing the geometry of the layout here. So I laid it out so you can see that the, and I'm dispensing with the 0.00 and the microfarads. I'm just putting the values. You'll see that you've got 2 identical branches of 5 and 10 in series on either side of the 2 microfarads. And then you have a 10 and a 10 below that. So, and I call this diagram A. You can see here I call this diagram A. And so I've got A, B, C, and D. These are the figures that I'm using. So the first figure is just redrawing the the main the figure 2512, where it's a little more recognizable as to what's going on. And you're free to do this. You're free to redraw the circuits so that you can get a better understanding of what's going on. Sometimes, once you get good at it, you won't need to do that. Okay, so the first thing we're going to do is we have to take care of the series, the 5 and 10 series. So if we do the C equivalent is equal to 4, C equivalent is equal to 5 microfarads. I'm using the easy method. I like it since there's only two, a 5 and a 10. The C equivalent is 5 times 10 divided by 5 plus 10. So it's basically 50 divided by 15, and you end up with 3.33 microfarads. Now, let me say something. Whenever you have capacitors in parallel, the equivalent capacitance should always be less than, okay, I misspoke. Whenever you have capacitors in series, the equivalent capacitor is always less than the least value you have. So here, the least value is 5 in this series. And so the 3.3 microfarads is less than 5, and we know we've done it correctly. If you would have ended up with 7 or 12 or something like that, you know you did it wrong, because the equivalent capacitance has to be less than the least capacitor in the series. Okay, so the C equivalent for that branch is 3.33. Now we have a parallel of 10 and 10. Well, whenever you have a parallel, you just add them together. So 10 and 10 is 20. So now in B, I've redrawn the figure A as figure B using the substituted values. The 3.33 for the 5 and 10 series circuits, and the 20 for the 10 and 10 in parallel, right there. Now we have to combine these parallel, and when they're in parallel, you just add them together. So the parallel with the 3.3, the 2, and the 3.3, you add those together, you get 8.66 microfarads. So now we have 8.66 and 20 in series. That's C. So now we have to solve this series with 8.66 microfarads and 20 microfarads. So the C equivalent is the product divided by the sum, and it's 8.66 microfarads times 20 microfarads divided by their sum, 8.66 plus 20, and you end up with 6.04 microfarads. So D is the equivalent circuit of this whole big mess up here. It all reduces to 6.04 microfarads. Now, what is the charge on C3? Well, the C3, C3 is that one there, which is this 2. How we're going to get that? Well, not to worry. We just work backwards. We look at the charge on C3. Let's work backwards. The total charge using figure D is Q equals C times delta V. So it's 6.04 microfarads times 60 volts, and you end up with 362 microcoulombs. Now, that 362 microcoulombs has to be spread over these. That 362 microcoulombs is going to be this. It's not spread over. It's the same. Once you get 362 microcoulombs here, you're going to get 362 microcoulombs on the other. So that both of these experience 362 microcoulombs. What's going to be distributed among them is the voltage, and that's what we're going to calculate. So we have 362 microcoulombs. So the voltage on each capacitor in C is the delta V for the 8.66 is 362 microcoulombs divided by 8.66. You get 41.8 volts. And the delta V for the 20 microfarad is why do I have 5? It should be 20. That's from an error I had earlier. Let me change that real quick. Sorry about that. This should be the 20. So for the 8.66 microfarad, it's 41.8 volts, and for the voltage across the 20 microfarad, you get 18.1 volts. Now those should equal to 60 volts, and they don't. 59.9 because there's some rounding error, and I'm not gonna worry about it. But it I got close. 59.9 is close to 60. Just some rounding error from my calculations. But you can see that it's close. Now, the voltage across the upper parallel is 41.8 volts. So there's 41.8 volts. I'm sorry, 41.40. I talk faster than I write. 41.8 volts here. And what was the other? 18.1 volts. 18.1 volts here. So that 41, running out of room, for that 41.8 is across this upper branch. Now, it's 41.8 across the 3.3, across the 2, and across the 3.3. Really, the 3.3 is just a 5 and 10, but we're only worried about this 2 here. So let's, since we have 41.8 volts across this upper tank, I'll call it, that's all we have to calculate. The voltage across the upper parallel is 41.8 volts, so the voltage across C3 is 41.8 volts, and the value of C3 is 2 microfarads. So the charge on C3 is equal to 2 microfarads times 41.8 volts, and you end up with 83.6 microcoulombs, and that is the answer there. It's a little tedious. I mean, it took 2 pages to do it in 4 figures, but if you just do it step by step, you can get it done. It's a little tedious, but it's doable. So that's how we approach these parallel and series circuits with capacitors. I did say that whenever you have a series circuit, like we had the 5 and the 10, the equivalent capacitance for series is always less than the smallest value. Whenever you have parallel, it's always largest than the largest value. Well, in this parallel, we had 10 and 10, and we got 20. In this parallel, we had 3.3, 2, and 3.3, and so that, what did that add up to? That added up to 8.66 microfarads, and 8.66 is certainly larger than 3.33, which is the largest value. I hope this helps. I'll assign some homework for you, but this is a good run through of what I expect you to do on these homeworks. Okay, let's stop the share.